the autorhythmic cell and the contractile cell, then anytime I generate an action potential, the contractile cell will generate an action potential. A different one, with a long phase plateau and everything, but I have action potential. But I don't reach Miranda. Miranda is over there. I just reach Kara, right? I'm here, and one of the cells next to me, one of the red cells is Kara, and here I have Miranda. So how does Miranda going to contract? She's going to tell me. Kara is going to let her because they have gap junctions between them. Remember? We just need to innovate a few cells because we have gap junctions. Each cell will stimulate the other cell. So the idea is that the autorhythmic cells generate the action potential, propel it to the neighboring contractile cells, and the contractile cells propel that to the neighboring contractile cells. In addition to that, the autorhythmic cells will propel the action potential from one to the next, and we'll talk about that shortly. Any questions so far, before we talk about how this whole thing is organized in the heart? Just about the concept of the gap junctions. Yes, sir.
Sorry, just to clarify, it's only the 1% of the autorhythmic cells that.
No, only 1% of the whole cells of the heart, of the muscle cells in the heart, right? That have connective tissues and so on, are autorhythmic cells.
Yes. Sorry, I misspoke. That's what I meant. So all of the autorhythmic cells, which make up 1% of the heart, those are the only ones that contract spontaneously or generate action potential spontaneously?
Exactly. They are the only ones that contract spontaneously and show this type of potential.
And
all the others are cardiocytes that show, where is it? This type of contraction, of action potential, the red one, which is very different, right? Okay. So let's now see how it works, how we propel. It's not happening all at once and in all places because that will not make any sense. You'll have each place of the heart contracting independently of the other, right? So we want to make some hierarchy and order are key here. The key one that starts it all is a node, remember a cluster that is found only in the right atrium. It's not symmetrically distributed, only in the right atrium. And it's called the sinoatrial or SA node. Collection of autorhythmic cells that can generate action potentials faster than any other part of the heart. The faster is a key here. Imagine yourself a parade, a Christmas parade, right? And you have, up there in the front, there's the person with the, I always forget how we call this, baton, is that the word? The drum, help me guys. The baton, right? And it's a drum major, something like that. How we call this? You know, the person the first that says that basically lead the parade. Okay, I'll just call it the person that leads the parade. I thought it's a drum major. This is what people told me, but I'm not sure. Okay, so now imagine that you have this whole parade, and everyone is going in all of the autorhythmic cells, right? So everyone has their own pace. This will be a mess. This cell will contract, and now this cell will contract, and this will be completely uneven. So we need to have a leader. And the leader is the one who walks the fastest, and everyone is just following him. Why? Because the leader reached the threshold faster than the other. They all have the same threshold. But the leader is the one who reached the threshold faster, so depolarizes first. So when they, not secrete, but when they propel the sodium ions and those go to the other cells, that will determine the action potential. They are the ones who dictate the pace of the action potential. All the others are slower. They are autorhythmic cells by themselves. They can be spontaneous, but they actually respond to the hierarchy, to the faster one. That's the SA node cell. The SA node is therefore what we call the pacemaker, because that will be the one determining the pace of the heart contraction. It determines the heart rate, which in other words is the number of contraction, or as we're familiar with the word beats, right? Per minute. That's a rate. We need to provide a time factor. So when we say my heart beats, let's say 60 times per given minute, that means that your SA node of arrhythmic cells generate an action potential 60 times per minute. Yes? Autorhythmic cells. Yes, but it will dictate, since as we will see, it's going also to talk molecularly with all the surrounding muscles, right? So it's going to determine the pace of the contraction of the entire muscle. So there are two paths at work here. One from the yellow cells to the red cells, and the other one from yellow cell to another yellow cell to another yellow cell to another yellow cell. Yes?
So you're saying the SA node is internally controlled, and how do you
So Sierra is asking, how do you increase your heart rate? What do you think? Even, we'll talk a lot about it, but right now, what do you think? What can you do? Who will make the heart work faster, for example? The nervous system. And the nervous system is going to do that by going to the SA node and say, work faster. That will be a stimulus that will not turn it on, but will turn it up, or will slow it, will make it slower. We'll see how it works. Inhibits or promotes. But we'll talk a lot about that, about regulation of the heart. Okay. So let's just go over steps, and every now and then I'll stop and ask you some questions, and we'll make sure we follow this path. Okay? First of all, remember, again, everything in yellow represents the autorhythmic cells. The red, purplish cells of the walls, they are all tons of cardiocytes, and the blue is the inner part of the chamber. Atria or ventricles. Remember that the cells connect via gap junctions. So the first part is what we just discussed. SA node in the right atrium generates an action potential, AB is action potential, that travels via gap junctions to the AV node, that's the next one. It also travels to the neighboring muscle cells, blue from this side, red from that side, and basically tell them contract. But we're focusing now on the conductive system. We'll come back to the contraction later on. It also goes to another part. You see the dashed line. The dashed line is beyond. You cannot see it because it's behind the aorta. Going to the left. Why is that? Why do we need that part? I need these muscle cells to contract as well. They unfortunately do not have their own node, so the SA node needs to travel to propagate the action potential all the way to the left part, which this is exactly what happens. You could have imagined that maybe it would have evolved with two nodes, but this is the way it evolved. And it's working, basically. Pretty much alike, most of us. Any questions so far? So, the action potential continues here, right? And it will continue, these are the arrows, the conductive system will continue with that. But let's talk for a second about the muscle, the contractile cells of the muscles, right? And now imagine this is my laser point, SA node, action potential, action potential, action potential, action potential, action potential, action potential. And this is the floor of the atrium, right? And also the ceiling, if you will, of the ventricle, right? Of the right one. But the same thing goes in the left one. So if I have gap junctions between the floor here and this part, the action potential will go from this part, the laser point, to this part. Hopefully you can imagine that because beneath those extensions here, right? But actually here we don't have gap junctions. We don't have gap junctions that connect the atria, left or right, with the ventricles, left to right. I want us to think together, what if we did have gap junctions? Why don't we have gap junctions? So Diego, but let's think about it, okay? What do we get from not having gap junctions? Everything will be faster, will be much more efficient. Why not? Which do not exist between the atria and the ventricles. Anyone has any idea? You want to share what you thought in your groups? Yeah.
So what we were thinking is that if you had gap junctions there, when the atria would start to contract, it would lead to the ventricles starting to contract
Wonderful.
before the blood is ejected from the atria, and then what would happen is you'd kind of have some like backflow of blood back into the atria.
Okay, so the idea is a backflow. We don't really need to worry too much about a blood flow. Why is that? A backflow. Why is that?
It's the valve.
Because the valves are structured anatomically in such a way that it will prevent this if everything works well. But if I don't have a gap junction, or I don't have gap junctions in plural, then, so if I do have gap junctions, then the atria and the ventricles will contract almost simultaneously, right? Remember, one single unit. If I'm in the ventricle now, and let's say I contracted, and now I'm waiting for a refill. Okay, we're done with the all absolute refractory period. Now the ventricle is contracting, but I'm immediately contracting. I need some time to get refilled from blood from the atria. The ventricles get their blood from the atria, right? So, and we provide the blood through the contraction. So what we want to make it optimal is for the atria to contract, and then just a tiny bit of a short delay to allow the ventricles to get filled with the blood, and then let's go ahead and contract the ventricles. We need a short delay. Diego, you had a question? No, because the left and the right are going to act almost simultaneously. So you don't need to consider even the very small difference that we have between the left and the right. Yes? Okay, so the next part, we need a delay first, right? And we don't have a gap junction, so we have to continue. What makes the delay physically? The SA node travels the propagate the action potential towards the AV node. It goes either through the muscle cells, and you can actually see that there's also a direct connection. So we need to stop at some point, and the AV node is a traffic jam. That's the one responsible for the delay. So some regions do not have gap junctions. I highlighted that because that's how we're going to control. That's how we're going to make not really a one single unit, but two different units. Atria all together, and then ventricles all together, but two separate units. By removing what? The factors that allowed everything to work in unison. So the second part is exactly what we just discussed. At the AV node, the impulse is delayed. So if you look at the laser point, it's kind of like the action potential. It's going to go quick, and then it stays. For, of course, it's very slow. It's very quick anyhow, but it's 100 milliseconds, or 1.0 second. And that will allow for the atria to start and complete the contraction before ventricles contract. The ventricles are still waiting. Yes. Because why is the AV not the SA? Because you want all of this part of the atria. I'm just showing you the right. The same thing goes for the left. Okay? You want it to contract in unison. You want that immediately after the SA contracts, then all the cell will be one after the other immediately contracting. At the end, what I have is the AV. Now what I want is wait a little bit before we continue later on. Andrew? No, it's just AV right here. Okay, let's continue with our conductive pathway. Any questions again? So we have a delay in the AV, right? We're focusing on the conduction, and every now and then we talk a bit about contraction. So from now, okay, we waited a bit. Now it's time to propagate the action potential towards the ventricles, right? So we continue. And it's in the third part, okay? From the AV node, the impulse spreads to the bundles. Okay, we call it the bundle of His, and it splits into two, one to the right and one to the left. As Andrew asked, we don't have an AV or an SA in the left side, so we need to take care of the left and the right from the AV node. So what do? We branch them right here in the middle of the septum. One is going to be responsible for the right, one branch, and one to the left. And that's going to go all the way to the bottom, and then it makes this U-turn to the Purkinje fibers. But before we reach the Purkinje fibers, there's another challenge for you. What if challenge? To think about this. This is a great machine. You need to think why it's acting so optimally. So we learned that there are no gap junctions here, right? So it will make sense that, okay, we stayed, we waited, everything is cool, we took care of the whole delay thing, right? Now we can have gap junctions not just between one yellow cell and another yellow cell. Remember, yellow cells are autorhythmic cells. But now gap junctions, like we had before, between the conductive cells and the neighboring red labeled cells, the contractile cells of the ventricles, right? But we don't. We don't have gap junctions between, we do have gap junctions between one yellow and the other, so we will continue with the conductive system. but we don't have gap junctions here and here and here between the yellow and the red. Where do we have gap junctions? Only after we make the U-turn between the Purkinje fibers. It's the same Purkinje, whose name is actually Purkinje, but we call it Purkinje here, okay? The same from the Purkinje from the cerebellum, but now we're focusing here, okay? So Purkinje fibers, electric action potential doesn't go just up, but also goes to the contractile cell to contract them. So here's my next question. Why no gap junctions between the bundles, the orthorhythmic cells of the bundles, and the neighboring contractile cells? I want to remind you, we waited, we had our delay, we solved it already with the AV. So why not, okay, we made it, let's start contracting. Let's think about it together. Okay. So then it's suggesting a war. It's not actually going to be a war because the two bundles are independently contracting. You can have gap junction just from to the right and to the left. We're good with that. It's a good idea, a creative idea, but there's not a problem with that. Anything else? Try to imagine what would happen if we did have gap junctions there. I'm here at the ventricle, right? I got the action potential. This is the top of the ventricle. Imagine it here, okay? So if you guys, I'm going to do it here. Okay, this is the top, this is the apex, the bottom. Okay? I'm now going to get an action potential. I do have gap junctions in my scenario, okay? What if like scenario? I'm contracting. How is contraction going to go? Top, right? And I'm doing this because it's simultaneously, but it takes a bit of time until it propagates, right? I'm going to contract. Where's the blood going? To? What do we have at the bottom? Dead end. Nothing. Wall. Apex. Where's the pipe? The pipe. So we just push blood to nowhere that is going to create turbulence and going up. Instead, what am I doing? Is this. If you can watch me again. Okay? I'm propelling the action potential with no contraction. Just action potential, action potential, action potential. I'm reaching the bottom. Now I'm moving up. Now immediately contraction. So I'm pushing the blood from bottom to out. Pulmonary trunk, aorta, the pipes. So the last part of this is the impulse after the U-turn sweeps to the ventricular wall via the Purkinje fibers. Here you have lots and lots and lots of gap junctions between the Purkinje fibers, the orthorhythmic cells, and the neighboring contractile cells of the ventricle. I'll see you on Thursday.